at absolute zero. Okay, so you do this, and there's no thermal energy, so the plane would not relax. So everything is frozen. You cut it, and that exposed face will become your surface. Okay, so therefore, what we think about is that this surface, after you cut it, will be exactly at the same position before and after you cut your bulb. Okay, so that's the first thing we think about ideal surface. The ideal surface that we created this way can be explained in terms of this TLK model, terrace, ledge, and king model. A terrace is a very simple idea. The terrace is just a flat area, and a ledge is just a step, a narrow strip of boundary, if you like, step boundary between two terraces, and a king is the irregular twist in the ledge. So to give you description, so this is my terrace, this is my cutting, right, just simple cutting of my space. So everything stay put, no reconstruction, ideal surface, we don't allow reconstruction. So in the TLK model, the terrace is this flat area, the ledge is this highlight in blue, the step boundary, right, between terraces, and then a kink is in the ledge, but it's twist this little point along the ledge or step boundary that you have, then that's called the kink that you got. Okay, but of course in real life, technically the TLK model should contain defects, because sometimes you would allow it to relax, and you may have little defects like this. There's an expansion at this point, and there's a bump on this point, things like this in terms of the defect. But we don't worry about it. I just want you to know the terminology between terrace, ledge, and king, and this is the definition that we have. And if you think about it like that, in a very simplistic way of this TLK model of a surface, so this is another TLK model. So you have a terrace in here, and then you have a ledge, and then you have king inside the ledge, like this. Of course, in a real surface, you can sort of describe it also like this. There will be defects, and there may be some new atom. There may be vacancy, missing atom in your terrace, and stuff like this could occur in your real surface from the ideal surface that we just mentioned. So if you think about the TLK model, so you can think all three surfaces go into, all the surfaces can be classified into three ways. Singular surfaces, which are simple terrace, right? They usually correspond to low Euler index plane of a bulk lattice, so it could be 100, 111, and so forth. And they are smooth on the atomic scale. So these are known as singular surfaces. Racino surfaces are sort of slightly more complicated than singular surfaces. They are sort of a mixture of singular surfaces separated by step boundary. So here I say they are finally removed from singular orientation. Singular orientation means 100 or 111, some low mu indexes. And they consist of terraces of these low mu indexes separated by step. And so usually they are known as step surfaces that we have. Okay, so let me just, instead of reading this to you, let me just show you the picture. So here we have singular surfaces will be just one of these terraces at infinite time. But normally you don't have this. You may have terraces separated by well-defined step with right periodicity, you see, with periodicity, regular periodicity, and that creates so-called step surfaces, just like your staircase that you have, right? So these are called racino surfaces, right? Consists of singular surfaces separated by step boundary like this. Now, of course, if you warm this thing up, so these are sort of idealized, meaning that they are sort of at absolute zero. And if you warmed it up, what happens is that you roughen the surface. The surface starting to, the atoms starting to move because you are introducing thermal energy. You would create something called rough surfaces. That's the third type of this in the TLK model. They are totally disordered. So if you warm up a surface like this, first of all, the step boundary will start roughen, will start moving around like this. And then eventually it becomes like this, a totally roughened surface like this. So you go above the roughening temperature and you become like this. Okay? And so again, singular with single, which is sort of slightly more complicated than singular. And finally, rough surfaces in this model. But TLK model does not allow for relaxation, and surface is ideal. In other words, you don't allow reconstruction. You don't allow the atom to move about to the most ideal point. You don't. You freeze every atom on this surface, or any kind of thermally induced effect. So this is a point to note about this idea. So, but it's a good starting point for us to think about surfaces that way. These are the surface structure can be thought of as happening at 0 degree or 0 Kelvin. There we go. Okay, so now I like to sort of introduce the idea of surface crystallography. So we talk about in simple-minded way what is a surface. Now we want to talk about surface crystallography, just like our crystal crystallography that we studied a couple of lectures. Okay, so